Good morning. Am I audible?
Yes, you are audible. Good morning.
Good morning.
Good morning. Proloy, I have sent you Abhishek's institute ID. Please
Yes,
add him to
I
Teams.
think that.
Please add him to Teams. How many have joined? Have all come?
So 84 including us.
$84. We have 121, right?
119 yesterday I have seen.
Okay, today morning it was 121.
Okay.
Okay. Is the presentation visible?
Yes, it is visible.
Okay, so just tell me when I should start. It is 5 minutes. Should we start? How many are there?
Yes, we can start. It is increasing. So 96 last.
Okay, good morning, students. Welcome back to the online semester. I hope you had a good break. We are meeting after a couple of months after the software engineering course. And this will be another very foundational and extensive course, and you learn some core technology in computer science here. So as you know, we are going to talk about compilers that you have been using for so long, at least since your first year. And now you will have to build one. You'll have to if I say one line target or take back from this course, it is to build a very tiny version of GCC. So at the end of the course, each one of you would have your tiny GCC with you, which would behave almost like the GCC that we get from GNU. So I will start with a few basic information on the course. The slides, presentations for this course material. For the course, all presentations that me and Professor Mitro use would be uploaded to the CSE Moodle server. Already the accesses and all those have been shared with you through the mail. And these are the books that you can refer to. Of course, the first book by Aho, Lamb, Shetty, and Ullman is the kind of the Bible, the Gita, the Quran for this particular course. It has almost everything, but at places we go beyond what this book says, because as you can see, this book talks about principles, techniques, and tools, and we go beyond to implement many of these techniques using many of these tools. So you can refer to Flex and Bison, the O'Reilly book, for the two major tools that we use. Or you can check online references also. There are quite a few of them. Compiler Design in C by Holub is an old book, but it has some very good insight into the course, into compiler building in terms of different data structures, different implementation details, and so on. And for advanced topics like parallelizing compiler or building compilers for multi-core systems and so on, the Mushnick's book is very good, but we may not have much time to discuss many of those issues. For this course presentations, we have borrowed quite a few slides from Professor Srikant's NPTEL compiler design course with his kind permission. Timetable, there is a provisional section allocation, section 1 to me and 2 to Professor Mitro, but we will handle the entire class more on the task basis than on the section basis. You are already on the Microsoft Teams, and we will soon create a course has happened. We will post the recorded videos on YouTube. By the way, Pralay, are we doing the recording? If we are not, then you may please turn it on.
Yes. I switched on recording.
Okay. Thank you very much.
It's being recorded.
Now, coming to evaluation, most of you were in the software engineering course, so you'll be shocked to see that in the theory course, we do not have the bombardment of assignments that you had in the software engineering course. And that's particularly because unlike software engineering, where we were doing laboratory assignments on different aspects, here it is a very focused set of laboratory assignments that will be there. So in theory, we will primarily focus the evaluation based on 3 class tests, roughly covering 75% of the total weightage of the credit. And we will have one assignment towards the end, which will be kind of, so this 3 class test covering 75% is kind of, everyone should be able to do very well in this. And then we'll have a little advanced assignment, one assignment towards the end of the course of 25%, which will deal with some of the features which you may not be able to implement in the laboratory, but you would have learned in the theory course. So we'll have a separate assignment on that. Obviously, attendance is compulsory. I'm sorry. Regarding the laboratory course, the slot is from Thursday 2 to 5. Usually we will start the session whenever we meet online from 2:30, but we will have regular announcements. And it will again be on Microsoft Teams. In the laboratory, we will have a series of assignments which will cover roughly 70% of the credit. And we will have 2 separate laboratory quiz, which will 15% each, which will take the 30% of the remaining credit. Whenever we have the class hours in the laboratory, it is mandatory for attendance. And you have already attended the software engineering course, so you know that we have zero tolerance to plagiarized submission. If it is found that 2 or more of you have plagiarized submission, identical copies or near identical copies and so on, then we will be forced to evaluate all of them as with 0 credit, not looking into who has copied from whom. So take care not to copy, and take care not letting others to copy from you. Coordinating platforms, we have already given, Professor Mitra has already circulated the CSE Moodle details, which will be used for, as I said, the lecture material as well as for conducting the different tests, different quiz and class test. Announcements will be made on Moodle, so keep on checking. In addition, oftentimes we will use the ERP for communication. So you should make sure that your registered email at ERP works, otherwise we'll miss out on those. The submissions for assignments, you know this from the software engineering course, the submission will be accepted only through Moodle up to the specified deadline. So please do not send a submission through mail to either of the instructors or to the TA. We will not be able to take that. If you are late for a submission, ask for an extension, and we will extend it for you with obviously some penalty on the final credit. Normally, our principle is late submissions with permission for up to 3 days will be allowed with 10% penalty on the credit that you earn. Exceptions to these would be on medical ground, of course with proper medical certificate, or on tasks that are taken up for the institute, like representing the institute or something like that, with Dean's proper permission and prior notification to us. You know all of these procedures we have followed in the software engineering course. In the theory assignment, as I said, there will be one assignment towards the end. It will be individual, and you may need these, or most of it may be on paper also. For laboratory assignment, we will have 6 assignments in total. Of that, the first 2 assignments will be individual. You have to individually do and submit. Then you will have to form groups of 2. You'll have to select your partner and form the group. The TAs will execute that procedure. So assignments 3 to 6 will be in groups of 2. So every student or group will be assigned a TA, which may change with assignment, but this is the overall procedure. There is a strong continuity between assignments 3 to 6. That those are the 4 assignments actually where you build the compiler. So it will not be good to change your group structure during these assignments. So choose your partner with that view in mind. The language will be C++, platform will be Unix, Linux, And these are some of the tools that you will have to use, which are free, available on GNU. You build the compiler for C, but not exactly C because it's too huge. So we will provide you with a specification for a very, very, very small subset of C that we have designed. We call it the tiny C. And with that, you will, for that, you will build the compiler through assignments 3 to 6. And your target architecture would be x86-64. We cannot accept assignments done on other architecture because we will not have the infrastructure to check your assignments. This is a tentative schedule of things to happen. There may be some, there would be some changes to these dates and maybe some typos. Professor Mitro has just now pointed out to me that 17th November, the date given for class test 3 and lab quiz 2 is a Wednesday. It will have to be on a Thursday. So we will before we upload, we will recheck and correct those. So your first assignment in the laboratory would be annotating an assembly. So the first kind of prerequisite for this course is you understand the x86 assembly language very, very well, because that is the language into which your compiler is going to generate the final target. So we will have an assignment to check that you are understanding it well. And the way we do it is we compile a C program, small C program into x86 assembly. And after doing that, on the assembly, you will have to mark which part is the translation of which statement in C and so on. Second would be to create your library. This is required for implementing the compiler later on, because when you implement, you need a basic support for input-output, the I/O. So like what if we talk about C, it is printf, scanf, for at least basic data types like integer and string. So we will show you how to create a library using the assembly, and you will have to create your own input-output library, which later on will be used in your assignment. Then the 4 assignments, lexical analyzer, parser, target code generator, and intermediate code generator, that is 3 address code generator, and finally the target code generator in x86 will be one after the other, which will kind of goes in a bootstrap integrated manner. And finally, by the end of assignment 6, you will have your compiler for tiny C using your own library. So as I said, 1 and 2 will be individual and 3 to 6 will be in groups of 2. Here I have shown roughly the week allocation. I mean, how many weeks you are given for each assignment. The dates may not match that because we have breaks and all in between. Besides that, 3 weeks have been announced for tests. So we will have the 3 tests during this time. So the first will be on September 9th. Tests will be conducted during the laboratory hours. We have 2 to 5, 3 hours. So if we have class tests, that is for theory and lab quiz both, then we will split this into 1 hour 15 minute, 1 hour 15 minute within that 3 hours. Otherwise, we will just have only one. The second class test would be here, and the third would be here. The dates will again be checked and then uploaded. We have an announced autumn break for this week. So you will see that the intermediate code generator shows assign and submit date gap, which is a lot more than 3 weeks because it subsumes the autumn break where we are expecting you to take a break and not work. Finally, there is on theory, we will have an assignment, as I said, on the later on topics, particularly around optimization, which will be given to you towards the end of the course. And you will have to, I mean, we may be able to extend this date a little bit more. We will see on that. But this is an assignment which we'll have to do individually again to come. These are the dates on which we have holidays. So I think some of these, like 19/8, we may not be able to meet. There's a Thursday, there's a Tuesday, there's a Thursday, which is this is actually, this period of what is known as the Sera is actually within the autumn break, and so on. So we will follow the calendar as it comes. Finally, this is the list of TAs and instructors. You have our contacts here. The details of the TA's contacts will be filled up. I did not get time to put all that data. That will be filled up before we submit this, before we upload the presentation. So normally, if you have to contact, a normal procedure would be to send email. Do not call unless it is absolutely necessary. If submitting email does not work, the next step should be to send a WhatsApp or an SMS message. I would hope that all the numbers being given have WhatsApp enabled on them, so you can send WhatsApp. And only in a very extreme situation you should call somebody, because everybody is busy in their own spheres as well. So these are the important dates. Again, we will check. 17th November, I'm told, is wrong. We'll correct that. So that's about the basic course information. I will stop here and let me go back and check if you have any queries. Anything that you want to ask, anybody? Mr. Mitra has already addressed a few concerns. Some people are concerned about plagiarism from the very beginning. That is interesting. Just don't worry about percentage. Just write your code yourself. And if you have to copy or adapt from some open code base, which is not related to your assignment but may help you, please put that in the comment that this is from where this particular function has been taken. So that will take care of it. It is not the arithmetic of percentage that we are working on. I do know that there are several ways to beat this plagiarism checker. We are not talking about all that. If it is plagiarized, and if we see that you have plagiarized, it is a plagiarized copy. You may have done it, or somebody may have done it from yours. Then we'll have to take action. That you'll understand. Right? You would not want someone to get the same credit as you are after you have put in a huge amount of effort and that person has just taken your own. Right? So it's just protect your interest. Any other question?
Sir, how did we handle Unix? So there is a question and it is valid. So one student has asked that how will we get access to Unix platform?
There are several platforms available online. There are several online platforms available. GDB has a platform which is online. So there are two ways. One is you can have a dual boot in your system. You can do a VM and all that, which many of you would be able to do. We can check if some server accesses can be given, but I'm not very sure because there are a lot of network entry protocols inside the institute. So I would advise that if you are not being able to do it on your manage it on your machine with the VM and all, you should try and look at the online platforms. Other than that, Pralay, I think we can also look into if there are alternates and alternate solutions that we can provide them. Obviously, we should be able to do that.
Okay, so my suggestion is that actually I'm not sure. that first of all, how many, so may I just quickly take a vote? I have Linux. So can you please like in the comment, I have Unix or access to Unix somehow, so that we can quickly check that how many of you has the access to Unix.
Or can create one. You may not have it right now, but you can get it done.
So this is the first one. Two other options you have with you. One is that as PPT suggested, you can make your system dual boot. Another, have you heard the name that Oracle VM VirtualBox? So using Oracle VM VirtualBox, actually you can install a Unix in your Windows system. So we have only very few candidates who has the access to Unix.
Yeah, because I mean by
Right.
the next class, lot more will have, because they have not done it, so they will explore and get it done. They are computer science third year students. They cannot get stuck with something as trivial as Unix. So and Mac OS Sadvik will not work. It has to be on Unix.
So what I'm suggesting, so Oracle. So you can try this one. So if you have any problem, then we can have a session on how to install Oracle VM VirtualBox in your Windows system, and you can work with the Unix. That is one option. That online platform PPT as mentioned is another option. And even after that one, if there is any guys who do not have the access, we will discuss and we will sort it out. Mac OS is fine, so you can try Mac OS. But we expect that you please avoid
the problem with Mac OS would be that it will be difficult for the TS to check.
No, that's what I'm telling. So you should not use the specific instructions from the Mac OS. So when at the architecture level we are working, you have to stick with the architecture that PPT just has mentioned. Okay. So otherwise, it will be a problem for our TAs. Our TA do not have the access to Mac OS.
No, it's not only the question of architecture. If the code is not totally portable, they're using certain system calls I do not know. Then their submitted assignment may not build properly.
Evaluated.
Yeah, that is the problem. It's not only what you explained is perfect. It is in terms of the targeting. Right. Targeting can always be done in x86 using macOS, but I'm more concerned is it should just have a identical build, because we get into a lot of issues with TS saying that it's not building, students saying it builds, and so on. So we want to make it sure that it is. And Proloy, what you can do is two things you could help with. One is you can create 1-2 slides which you can put in the course information about this handling of Unix, which earlier was not an issue, so we did not have.
Right.
And also when we meet on Thursday, you could just give a small tutorial on this VM installation, which I think would be the best option for everyone.
I will do that one. In our lab class, we will do that one.
Other questions, students?
Sir, I have a question in the platform slide.
Yes.
Please, can you move to that slide?
I will do that. Just give me a minute. This sharing part in Teams is very clumsy. Yes. This is the slide you said? This is
the platforms one. Yeah.
This is a platform, coordinating platform, yes.
Yeah, like in the fourth point you mentioned ERP will also be used at times of communication. So like ERP, exactly the ERP mail or the ERP registered emails?
Yeah, ERP has a send mail option. So where the mails go to the registered email account of yours in the ERP.
Got it. Okay, got it. And in
right. So at times what we do is we just want to make sure that nobody is missing anything. So general communications we send out also through this ERP send mail. All that you have to just make sure that one or two emails that you have registered, they are valid emails and you check them. That's it.
And can you move to the previous slide, like in the same?
This one?
No, in the platform zone, there were 2-3 slides, I suppose, that told about the.
Okay, let me go from the beginning. You just, this is course material.
Okay.
This is about compiler theory course. Clear?
Okay.
Compiler laboratory course. Clear? This was about the platform. This is about submissions.
Okay, yeah, about this one. All announcements will be made on Moodle.
Yes.
So like sometimes what happens is that we aren't able to check Moodle very frequently, but for the mailing part, we get a notification, so we are able to check it at the moment.
Yes.
So would we be mailed that there is an update on Moodle or something like that?
See, we cannot always keep on doing that, but that's why I said that normally important announcements like an assignment has been uploaded or an assignment deadline has been extended, this kind of, normally we would try to send out an ERP mail as well.
Okay, yeah, that also, yes.
Okay, so that is the reason I know for Moodle announcement, you need to get into Moodle and check that. So if we make an announcement at 11 midnight or maybe in the early morning, then you may not check it till the evening. So to make sure we try to but the details of the announcement may not be copied in the email again, right? Because announcement may have a lot of details.
Yeah, that would be fine. We just need to know that.
But we will always try to put out some mails through the ERP general mail so that you get the notification very quickly and you know that something needs to be checked. That is what I'm saying. So, but what happens every time that when you send out mails, you get some failures on emails. So obviously I do not know what to do with them because their emails are not valid. Or maybe there's a valid email which you never check an email, right? So I'm just requesting all of you that make sure that your ERP mail, whatever mail it is, and you can have 2 emails also, but whatever that mail is, that must be checked regularly and should be a valid one. Okay? That answers your question, right? Okay, I'll stop.
Yes, sir. Yes.
Any other question? So we are good with the basic course information, right? Of course, you can get further clarification during the next during the first laboratory session on Thursday, or I mean anytime during other contact sessions. So Pralay, can I move on to doing the actual
Yes, please. Yes,
technical
please.
course overview? Okay. So friends, these were all logistics part of the course, administrative and so on. So let me just start by giving a quick overview of what you are going to learn in the course in terms of the technical content. Is the presentation visible?
Yes, it is visible.
Okay, thank you very much. So the compiler, as you know, is a very complex software. So I'm just going to give you a very brief course outline here, telling you about the different phases or components that the compiler has. We have already talked about the book. So in this module, the main objective is to understand the outline and understand the phases a compiler has. Of course, in one module or one lecture, you will not be able to internalize the details of every phase, but you will, all through the semester, we will go through them and you will eventually learn them pretty well. So this is the basic module outline, which is on the left. So the first thing that you should be very clear about is how do you compile a C program? What are the different major components of software or utilities or tools that work collaboratively to give you the final executable starting from the source code. Okay? I've just put C as a representative here. You will please always keep in mind that if I talk about C, it also means C++, it means Java, it means Python, it means other languages, unless I specifically say that this part is different from a specific language. Right? So what you have in C is you have a C preprocessor, which which takes your source code, the .c files and the included .h files into them. What it does is processes the directives, preprocessor directives like hash include, hash define and all that, does textual editing and creates a totally flattened source file at the output, which if you take a specific output in GCC, it is a .i file, which is a C, very huge, it becomes a very huge C program because of the different system headers or the library headers that get included. And that is a clean file stripped of comments and all preprocessor directives taken care of. Then the main part of the compilation goes on in GCC, which by itself will have multiple phases, and our focus would be actually to learn this component, the compilation through GCC, which takes a directives free, comments free C program file and compiles it into the assembly language of the target system, which may be x86, which may be x86-64, it could be anything else, as the case may be. And that assembly file is typically demarcated in GCC as a .s extension. Then that assembly file gets assembled into the object file. Now, when we run GCC, we cannot see this happening separately unless you put specific switch to run a particular component. You just do GCC and so on. It does pre-processing, compilation, assembly, and would generate an object file, which is a .o file. Based on the system, these extensions can also be different. You can have a different extension as well. But this object file is produced for every source file that you have. So this part of the flow you see is for one source file going through the pre-processing, compilation and assembly and generating an object file. So if you have, say, 3 source files to work together, then you will have 3 object files corresponding to the 3 source files. And we typically call that as a translation unit. Translation unit is one which needs to be handled through these components as one unit. And 3 separate source files will be handled as 3 separate units. So there are 3 translation units, and that will generate 3 .o files. Now, you have included a lot of headers, library headers, your own headers, but at least for the library headers, you just have the function prototype or class declarations and so on, but you do not have the implementation details. So the implementations are already given and compiled and, as we say, archived into certain library implementation components, which typically we will say here is a static library. We'll come to other forms of library, dynamic library later on. And they are available in the system as .a file, somewhat marking that they are archived, in the sense that these files are, you will have multiple such files. So what it does is kind of these are actual executable code corresponding to the standard library functions and classes, and they are kind of zipped together as an archive. And you need that because in your object file you have calls to these functions, so you need those function bodies to be included, and that is the process of linking that happens. So your object files, now it is not one file, it is all the, if you had 3 source files, you have 3 object files, 3.o, and the corresponding static library, all are linked together, symbols are resolved across and so on, and you finally get one executable for your project. So this is the overall flow that we follow. When we do GCC, the whole thing happens together. Some system libraries get linked by default, they are predefined. Some may need to be defined in the command line with specific option that I want to link this particular library that I'm using and so on. So in GCC, we do not, in running GCC, we do not discriminate. But in terms of our implementation, we will just focus on the compilation part. We will just implement this part. We are not going to use pre-processing. We are not going to use, not going to implement assembler. Neither we are going to implement linker. So what we'll assume is these components, preprocessor, assembler, and linker, will be used from GCC. So it's kind of your final compiler will have a preprocessor which you take from GCC, assembler and linker you take from GCC, but you have replaced this compilation unit by your own compilation unit, which takes a C source translation unit and produces the corresponding x86-64 assembly. So that's the whole target, and that's the intervention in the compilation process that we'll learn. We are not doing the preprocessor because it's very similar to the compiler. It's just a simpler compiler, which is a text-based compiler, text rewriting system. We are not doing the assembly and linker, not because they are trivial, but because normally people don't need to rewrite the assembler or the linker because they are provided by the system anyway. And of course, in the course, we do not have enough time for that. If you have a systems course somewhere in your curriculum, you will learn more about this kind of system utilities. And please, at any point of time, if you have a question, feel free to speak out. In the Teams interface, I do not get to see your hands and all. So just speak out and tell me that I should stop and discuss. So if we look into the, now what I'm doing is I'm just expanding the compiling part. So you have a preprocessor, source code come to the preprocessor, and then rest of it is the blow up of the compiler unit. So it has a lexical analyzer, it has a parser, which work in a handshaking mode, and it uses a major data structure called a symbol table, which gets started being generated from the lexical analyzer, gets populated heavily by the parser, and gets edited and used in the code generator. So after the code has been generated, we'll see that it will be generated in not in one go into the assembly. It will be generated in some intermediate form, and then it will be retranslated into the final assembly. So at these stages, there are various forms of optimization that you do. Otherwise, if you just blindly generate a code, it will be very inefficient in execution. So you optimize all that, and then you get into the backend, which primarily targets to a specific system that you want to work with, the specific architecture that you are working with. So you can see that if you think about the language dependency, you can see that the preprocessor is dependent on the language you are translating. The lexical analyzer and the parser certainly depends heavily on that. The code generator is driven by those. But once that has been generated, we would try to represent that code in a way which is independent of the source language. So that if I have a compiler for C, I will need to change a lot of things in the lexical analyzer or parser to make it a C++ compiler. The code generator will need to change. But beyond that, I should be able to use the same strategies for code optimization and different of those things, which is really a very big chunk. And you can see that till this code optimization, before code optimization, you have influence of the source language, the language in which your program was given. In the backend, you have to know the target architecture, target processor to which you are targeting. So the backend needs to know that. The middle part does not need to know either the source language or the target. So that makes this kind of an architecture makes the whole compiler a lot more reusable. We normally, in the context of compiler, we normally use the term retargetable compiler. That's where you can change a few things and target it for a different processor and so on. We will see what these techniques. Now that same diagram I'm now showing in terms of the actual flow of phases. So a compilation process is multiple phases because it is a translator. So it is taking the input of a source program, which if you think of that way is necessarily a character string. And finally, it is giving you a target machine code in assembly, which is kind of a binary. So this whole transformation cannot happen in one go. There are several issues that need to be taken care of. And as you go through the translation process, you keep on, transforming, morphing your given source program into different forms till you finally reach your target binary sequence of code. So from character string, you convert that into a stream of tokens. That is kind of very roughly saying that if you have an English text, you have characters and words. So naturally, only when we are very, very young kids, we spell out the words and read it. Spell out the letters in the word and read it. After that, the words itself become something which it means. So this is equivalent of words in the language. We call it a token. And then any sequence of words will not make a valid sentence. So there are grammatical rules which make valid sentences. So this token stream created by grouping characters is then checked for sentential correctness, grammatical correctness. This is what you have done in learning a natural language, learning English, right? Learning your mother tongue and so on. It has the same structure. So this syntax analyzer looks at the grammatical correctness of the sentence and represents it in terms of a tree. I mean, by tree we will come to that, but that is an equivalent representation. So only if it is grammatically correct, it can be correctly represented. If it is not grammatically correct, it will be rejected and your process has to stop. Now, every sentence that is grammatically correct is a correct sentence in the sense of the meaning, in the sense of the semantics. If I say that let's say the goat eats, say, meat, or the goat can fly. A goat can fly. Goat can fly is a grammatically correct sentence, right? Because it has the subject, verb, predicate, and all those are in place. But it is semantically not correct. It's not a meaningful sentence. So there is a difference between syntactic correctness and semantic correctness. So we annotate the tree representation of the correct syntax with the meaning that is associated to make sure that it has a correct meaning and we can extract that meaning. So this is kind of the first processing of the whole thing, and then we represent it. So up to this point, from character stream to annotated syntax tree, things are certainly dependent on the source language, because if it is C, it has one kind of characters allowed, one kind of tokens, one kind of syntax, one kind of semantics. If it is Java, it is different. If it is Python, it is different. But once you have annotated syntax tree, which says that you have a semantically correct program, then you can convert it into an intermediate representation, which is just into a very simple programming language or data structure, which represents the corresponding semantics. The advantage for doing that is from this point onward, you will not have to be concerned about the source language information anymore. So if you have a different source language, you need to change these three modules, these three phases in your compiler, but subsequent phases will work perfectly fine because you have converted them into an uniform, very, very tiny programming language called three address code, or certain data structure which is uniform for all languages. Now this part which we show kind of coming down is typically called the front end of the compiler. Now once you have got this, then you have a set of optimizations. There are a lot of logic that can be optimized. For example, if I have at a stage 2 multiplied by x, I can do it by a multiplication, 2 multiplied by x. I can do it by adding x to x. So multiplication is typically a far more expensive operation. So if I find 2 multiplied by x, I would be better off if I do x plus x, because addition is less expensive. In fact, I can do even better, because I know if I shift x by 1 bit, it actually doubles in the value. So I can left shift x by 1 bit. So which means that if in my intermediate representation I had a multiplication by 2, or for that matter, by certain powers of 2, then I can replace them by shift and get a better code, more optimized code. There could be several variables, temporaries, which may not actually be required. I can remove them and do. And there are a whole lot of this is kind of one major meat of the compiler, the major section of the compiler, where you can use a lot of theory and analysis and optimize things. Now, it is still machine independent. You still do not know what is the target, and you have no reason to know what is the source. So this is something which is simple logic saying that what kind of optimizations are possible. So then you generate a target code. You generate the target code, means this machine independent program you convert into the assembly program of your target processor. So naturally, if you have done a left shift of X by 1 bit, there will be a corresponding shift instruction in the target machine should be, by which you replace, and you write that. Now there could be several optimizations which become possible because they are available in your architecture, in your target machine. Your target architecture may be powerful, so it may have very nice instructions to do things. Most of the processors today are RISC, reduced instruction set computer. I'm not sure whether you have studied them yet. If you have not, we will give you a little overview before we get into that, which uses a small set of simple instructions, but which can be very efficiently generated from the compiler and optimized. And many of these RISC processors typically go by load store architecture, where you load a value from the memory to the register, do operation, store it back. Directly do not operate with the memory. So these are the broad phases. So in the next couple of minutes, let me just quickly run through these phases in the front end as well as the corresponding back end with a very, very pathological small example. And mind you, at the center of this whole thing sits a central coordinator for the compilation process, the symbol table, whose task is to remember all symbols in the program, the variables, the functions, the classes, the members, and all of their attributes, the type of the variable, the size it might take, the possible memory segment where you will allocate it, its offset in a stack frame, all of these different things. So therefore it started getting populated from the very first phase, the lexical analyzer, and it typically goes through being populated with more and more information as you go through the phases and survives till the end. In some cases, you might have a version of the symbol table also embedded in your final target, your final output, binary output, particularly if you are building for debugging. You would like to retain that so that while the program runs from a particular memory address, you can map back, or particular register content at a point, you'll be able to map back to the high-level symbol that was there in your system. Right? So central symbol table has a major role in terms of this. Now, these phases. So let's start with handling a very simple arithmetic expression and assignment. We are converting centigrade to Fahrenheit. This is a very typical arithmetic assignment that you will write. So if you look into this and ask, then does this names make any particular sense? They actually don't, right? I mean, they are written as Fahrenheit, centigrade to be meaningful to the human. But as it is, I can say that this is just a Fahrenheit is an identifier and centigrade is an identifier. So I write them as a doublet, which in the first part of the doublet, it says what kind of word it is. Right? You remember that I said the characters are FAHRENHEIT mixed into a word, which actually is an identifier. So I say that I'm taking this sequence of characters and transforming it into a token. And I say, what kind of token? What is this word mean? It means an identifier, which loosely you can say is a variable. And there could be many identifiers, like I have centigrade. So I say, I just give a serial number. Later on, we will see how to actually handle identification or the name of the identifier. But I can just say it is ID1, centigrade is ID. What else we have? We have an assignment operator here, which is already known. Mind you, just you are doing grouping of words, so just having this symbol gives you assignment. But if you have two such symbols together, then you will get a different operator, right? Checking for equality. So you group in that way and you write the corresponding token, which is an assignment operator. Mind you, there could be any number of gaps here, or they could be side by side. You just ignore them because they are no more meaningful after you have done the conversion to the tokens. After ID2 centigrade, you have a multiplication operator. You say multop. Remember, the same symbol is used for taking content of dereferencing, but somehow we'll have to know what is what. That will come to later on. Do not worry about the fact that symbols are overloaded in many places in the language. This is simple multop followed by a constant. And from the existence of the period here in between 1.8, you know that it is a floating point constant. So you say its token class is fconst, and the value, because if it is a constant, you need to know its value. The value is 1.8. Then you have the addition, then you have the addition operator here. And finally, you have a iconst, which is an integer constant. So when you transform this given sequence of characters into 1, 2, 3, 4, 5, 6, 7 tokens, you have a token stream. That is the job of the lexical analyzer. Now you can see that I could have had a different, actual input expression. Total amount is assigned from principal amount into 10 plus principal amount. This is similar to the previous one, except that in the last token, here I have iconst 32. There I will have ID2, very same as ID2. Or I can have a little variant of this. Final velocity is acceleration times time plus initial velocity. Here it is different that this fconst 1.8 is actually ID3. 32, instead of iconst 32, you have ID4. But structurally, if you look in terms of the arithmetic, structurally, they are very similar. And the basic purpose of lexical analysis are two. One is grouping these characters into tokens. And that consequence of that is the moment you do that, you get a different kind of grammatical structure coming out of the whole thing, as you will see in the next slide. So these are the same expressions, assignment expressions that you saw in the last slide. I've just symbolized it shortly for ease of writing. And if I write in terms of tokens, this is what it means. ID assigned ID times num plus num. If I do not distinguish between floating point and integer constant. This is the second one is ID times num plus ID. Here everything is ID. Now I will say, okay, these are three different arithmetic expressions and structure, but actually each one of them has a characteristics of having a value. ID has a value, whatever that ID is. At the point of execution, it has a value. Num has a value always. So I can think of ID and num, I can generalize and think of ID and num both as expressions. What is an expression? You learned in C. An expression is something which has a value. So if I write it in terms of expression, it turns out to be all of them convert into the same structure. Expression assigned, expression times expression plus expression. Which means again that between these two operators, this times or multiplication has a higher precedence. So you can parenthesize and show that. So this is the value of the lexical analysis phase. Let us move on to the next phase. So this is the output of the token stream. I will lexically analyze, and I will put in terms of, I'm going back one slide, slide 9. Think of this is the, now I have got the stream. I need to decide if it is grammatically correct. So I'm trying to extract or put it on the grammar that I have by identifying the order in which the operators will be done in this expression. Obviously, there are 3 operators. You know that assignment in C is an operation. It's not a statement. The whole thing is an expression. It becomes a statement when you put a semicolon after this, right? So out of the 3 operators we have, multiplication is highest. That is, it should be done first. Addition is the next, that it should be done after multiplication. And assignment is the least, so it should be done after multiplication and addition. So, and all of these operators are binary. So I represent this fact. This is a linear structure. So to understand E assigned, E star, E plus E, or any one of the above assignments, I need to remember this, priority and precedence rule and mentally find out how to do this computation. But I can make it explicit by putting it into a nonlinear structure. Slide 10, which is a tree. So what is this nonlinear structure? Typically called a parse tree or a syntax tree. I have a node, every node has a value. Every node represents an expression, it has a value. Like here. Later on it may not be, but in this representation it is. So given the priority precedence of operators, what do I have? This has to be done. ID has to be multiplied. ID has to be multiplied by 1.8. ID2 multop 1.8. This has to happen first. So I create a node with this multiplication operator and 2 operands. This is a left operand, this is a right operand. What it means? That the value of this node is the multiplication of ID 2 and 1.8. That gives me the multiplication. The next is to do the addition. So I have to add 32. So I create a plus node which takes the result of the multiplication and adds 32 to it. And I get that result at the value of the plus node. Final is the assignment. So the left child is ID, ID1, and the right child is the result of this addition. I will assign this value to this ID. Now you can see that this tree does a lot of wonder. This conversion from a linear structure to a non-linear structure tells us very clearly it resolves all of your precedence and associativity issues. You don't have to remember it because it is explicit in the tree. Obviously, you cannot do an operation unless both of the operands have a value. So there is no way you can do plus before you have done this multiplication. You cannot do this addition before doing this multiplication. So it clearly says that the lowermost operators will always be done first, and the uppermost operator will be done the last. So it clearly embeds in the tree the entire structure of the precedence and associativity which we need to understand the assignment expression. So we have converted from characters to tokens, and now we have represented it in terms of it. We will call it a syntax tree, parse tree, an intermediate representation, which is clearly bringing out the order in which we must do the operations according to the rules of the language. Keep in mind that if I had, say, if I had ID assigned, ID blank ID, ID assigned ID blank ID. This is clearly wrong. That you cannot have a assignment statement like this in C. Now, when you tokenize, you will not see this. You will tokenize this ID1 assign, ID2, ID3. You will tokenize like that. But when you try building the tree, between ID2 and ID3, there is no operator, so you will not be able to build the tree. And that failure tells you that this is a wrong program. So I said that the syntax analysis has to do with the grammar of the language. And this is how it works, that if it is according to the grammar, it will be able to build the tree, the syntax tree, and you know that your program is syntactically correct. And it tells you exactly how to execute the program. So it is a completely different representation. As I said, that we will keep on transforming the program representation from one to the other in the process of translation, but it's a completely different representation from the way we normally see the program, but it does retain the total meaning, and it retains it in certainly a better way. Moving on, we will pass this on to the semantic analyzer. So the same tree we pass on and we check on the meaning. Now, what is the meaning? I have to, in the multiplication node here, I have to multiply ID by 1.8. So what kind of multiplication this has to be? 1.8 is a floating point constant. So if this multiplication has to take place, it has to be a floating point multiplication, assuming that ID is also a floating point variable. So the result of this floating point multiplication in the star node, in the multop node, is a floating point number. So when you look into the plus operator, you have a left operand which is a floating point constant. You have a right operand which is an integer constant. You may be aware that typically the CPUs will have two different kinds of adders. One that can add to integer values, one that can add to floating point values. But you do not have an adder which can add a floating point value with an integer value. So you'll have to do something about it. The best information preserving one would be to convert this integer into a floating point. Implicit conversion you had heard in the in C programming. Now this is where it is going to take place now. So you know that the given constant is 32, an integer constant, and your required constant is a floating point constant. So you will need to put another operator here, which is a unary operator, which takes 32 and gives you 32.0. Takes an integer constant and gives you a floating point constant. So after that, this addition will be possible. Now you can see between this syntax tree that you had and the syntax tree after putting int to float, what you get, they are structurally same. They are doing the same set of operations, but you have cleared the semantics or meaning of the constant. So if you had here, instead of 32, if your source code had written 32.0, you will not put this into float operator. You would not need to do it. So this is what is meant by semantic analysis, that structurally Many codes may be similar or same, but what does it have to do with the meaning of the program? Now, after this can be represented, the same information can be represented in terms of an alternate representation than the syntax tree, which we typically call as a parse tree, where we say that an expression is an expression times another expression, or an expression is an expression plus another expression. A statement is an identifier assigned an expression, like this. So what is an expression? At the bottom place, any identifier is an expression itself. Any constant is an expression. So if I have expression ID assigned, ID1 assigned ID2 times ID3 plus ID4, this will be the corresponding tree. The only difference with the syntax tree is, in the syntax tree, other than the leaf nodes, the nodes, other nodes are operators. Here, these nodes are some auxiliary symbols. So this auxiliary symbol E and S are used to mean the kind of entity that I have. So I say ID2B is an expression. So what is the value of this node E? If I call that value as result of the node, then that value is the value of B. The result is B. What is the value of this node ID3C is a child of E. So value of this node is E dot result is C. So therefore, when you multiply them, in the multiplied node, you have B star C as a value. Now the question is, where do you keep that value? A value cannot exist in the vacuum. It needs a memory location. So what you do, you think of having a temporary variable. So you say this E representing E star E, E multiplication E, or representing B multiplication C, will keep the multiplication result in a temporary location T1. And this temporary location you are creating for the purpose of translation. So the value of this multiplication node is T1. And if I write a code, T1 assign B star C, then I'll be able to evaluate that and get the value of this node. Let us look at the addition side. The ID4 is an expression. So E dot result for that expression is ID4, which is T. Then in the addition node, the expression is adding the left operand T1 with the right operand T. So it is T1 plus T. And again, you need another temporary variable to keep it. So I can say T1 is T2 is that temporary variable, the value of this expression of addition. T2 is assigned T1 plus T. So the value of this multiplication and addition after that is T2. And at S, all I need is the leftmost child is an identifier A. Then I have an assignment. So this will take the value on the right side of the assignment, which is T2, and assign to A. So that is A assigned to T2. So you can see that by transforming the syntax tree into a little bit different form of a parse tree, which again still represents your program. And by working out temporary variables for each expression node that has a value, and by following a specific order, because the order is determined by how the tree is structured, we actually have a equivalent program which says A assigned B star C plus D can be done as T1 assigned B star D, T2 assigned T1 plus D, A assigned T2. Okay. Now, the advantage of writing in this form, in this intermediate, is that these are very simple. And it is restricted that every such statement in this three-address code or quad is called a three-address code, which means that no expression, no statement here can have more than 3 address references. Like T1 assigned B stars, 3 addresses T1, B, C. T2 assigned T1 plus T, 3 addresses T2, T1, D. A assigned T2, 2 addresses A and T2. It can have less, but it cannot have more than 3 addresses. So A assigned B star C plus D is not in this form because it has 4 addresses. So this is this is the 3-address form, which is a very, I was talking of that it's a very simplified language that we will have, and that is this language. I mean, of course, there are more to add to this, more to learn, but this is the basic flow. And it is called a quad because to represent this, you need 4 information, 3 addresses and the operation that you are doing. In the example here, the operation in all 3 cases is an assignment, but it could be other operations like comparison, Goku, and so on. So this is the basic intermediate representation we are getting into. So the syntax analyzed code represented in the syntax tree is converted to through the parse tree to the intermediate generated code, which in the same way looks like this has to be, multiplication has to be done first. T1 assigned ID2 times 1.8. Then this will have to be done into float. So 32 operated with the into float goes to T2. Then the addition, T3 is T1 plus T2. And now it would have been very easy to write by hand, I know. But here, the whole thing is going in terms of a very structured, correctness preserving process. So the original expression of ID1 assigned ID2 times 18 plus ID3, or even the original Fahrenheit assigned centigrade times 1.8 plus 32 is now converted into this sequence of 4 3-address data. Now the question is it optimal, or can I do something better? Do I really need 3 temporaries? The answer is obviously no. So I can do some optimization here by saying that into float 32 is given constant. So I do not need to do this every time I run the program. I can evaluate it at the compilation time. And I know it will be 32.0. So T2 actually is 32.0. Once I know T2, I can replace it in T2 here directly, 32.0. And T3 is T1 plus T2, which is 32.0. And ID1 is assigned T3. So I can just replace this right-hand side in the ID1. So with this, T1 is ID2 plus times 1.8. And ID1 becomes T1 plus 32.0. So instead of 4, I now have only 2 instructions to execute. So this is the crux of what we mean by optimization. There are huge amount of optimization that are possible, but this is just core idea. So we come to the last phase, which is the target code. Okay, before that, another example, A plus B star C plus T. So on the left, the first translation. T0 is A, T1 is B, T2 is C, T3 is B star C, T1 times T2. T4 is T0A. This has the highest priority, so it will be lowermost in the tree. So this is the first thing that happens. Then it is left associative, so this is the next one that will happen. So T0 is A plus T3. Then finally, you get T5 is D, and you add. You can easily see that you don't need so many temporaries. If you have temporaries for this, T3 is not needed because T1 is getting used here. So T1 gets free, so you can free up T1, write the T1 here. Similarly, T4 you don't need. T0 is getting freed up, so you can reuse T0. And T1 is already been used already. So T1 is not needed anymore, so you can free up T1, T5 and use T1, and finally you can free up T6, use T0. So you can see that by the simple logic of whether a variable is needed any further or not, I can simplify and reduce the number of templates. Now we can reduce it further. I can say T2 is assigned C, so I can replace it right here. It gets shorter. I can replace D. It gets shorter. I can do even more. I can put T1 assigned B, so I can put B directly here. T0 assigned A, I can put A directly here, and that will get even shorter. And we'll be able to manage actually with only one temporary. T1 gets B star C, T1 gets A plus T1, T1 gets T1 plus D. And that is the beauty of the optimization. Now, to generate the target code, you have to do also a lot of different analysis, because all that I have shown are flat expressions. So there is no effect of control. There's a lot of control, condition control, there are loops and so on involved. So we will have to, for that we do a lot of analysis called the data flow control flow analysis. And we have to allocate registers, because registers only can finally work with the ALU, and do the code generation. So those all steps will be involved, but just to show you how this can get translated here is I'm using one register R2 for representing, for keeping the values. So what I first need the value of the ID. So I load that value into the register. This is the assembly of the processor for which it is done. It loads ID2 into R2. Then it has to multiply that with 1.8. And I can keep the same register to keep the result. So I say multiply R2 with R2 and 1.8. So it multiplies R2 with 1.8 and keeps the result in R2. Similarly, it does this by adding 32 to R2 and keeping the result in R2. Finally, it assigns it to ID1. So it stores R2 back to ID1. Right? So just one register, and this is a sequence of assembly instructions that you'll get. Right? So this is the whole process, and this is your basic translation process shown. Like, to start here with the lexical analyzer, you can go through and check further. And this is your token stream, position ID1, operator equal to initial ID2, operator plus, rate ID 3, operator star, literal 60. Gets into this syntax tree, syntax analyzer, which tells you this. The semantic analyzer, it has to convert it to float and do this. Then the intermediate code that gets generated, optimized code, and finally the generated. This is the whole flow. And that is what you are going to learn in this whole course. And so I would go if there are. So you can. These are some information given as to what kind of translation languages do and so on. We'll come back to that later. And let me just go back and ask, see if you have questions. Let me stop sharing. Are there any questions on this part? I mean, this is just to give you an idea of the phases, nothing else. Do not worry about you have not understood any part, how it will be done and so on. On which forms optimizations will be done. They'll be done in multiple forms. We'll have all of that. That is the purpose of the course, but I just wanted to give you an overview of what the course talks about, so that you have, I mean, anytime you open this, phases, you will know exactly where you are in terms of learning the compiler. Is there any question? No questions? Have I put you to sleep with a long monologue?
I have one question, sir.
Yes, please, go ahead. Tell me.
Sir, so the code optimization, is it done on the expressions or on the quad?
As I said, it is done in multiple forms. Right? Typically, it will be done on quads. It will again be done on the assembly or before the assembly. So some optimizations are machine independent, like 2x, 2 times x can be replaced by left shift by 1 bit is machine independent. It does not depend on which machine, which language you are talking about. This is a mathematical certainty. So it can be optimized in multiple, I mean, in the machine independent place. But there are several in terms of what kind of registers you have. You may have special purpose registers, you may have special purpose instructions. There are a lot of things which are specific to an architecture. So those optimization can happen only in that assembly. Now, typically by expression, if you mean that when I have the original source language expression, typically you will not try to do an optimization because it's not easy, because you have not yet understood if it is grammatically correct and what does it grammatically mean, because you need to understand the grammar and the meaning before you can optimize. Right? Unless you understand what it means, how do you optimize? Do you get that answer?
Yes, sir.
So the kind of optimization that we do as programmers, we'll say, okay, instead of writing this expression, I can write it in that way. Right? It makes it better. That kind of optimization at that level is not possible, because you are using a lot of other knowledge in terms of. For an automated system like compiler, I need to go down to the level where I have a representation which is syntactically correct, semantically meaningful. Only then the optimization is defined, which says that keep the same semantics. What is the meaning of optimization? Can I make any change? No. I need to make a change which is semantically equivalent. It must mean the same thing. It must computationally do the same thing. but use less resources. When the resources could be storage, memory locations, temporaries, registers, or it could be time, that is using less expensive operator, using addition in place of multiplication when possible, using shift in place of addition when possible, or using less number of operations to do the same thing. It could be time or execution time. It could be something different like power. Several optimizations do not look at these, they look at power. The compilers that compile a code on your for your mobile device, handheld device, often has to worry about the power most. Other than your system stack in your mobile, the call stack, the GSM, etc. Rest of the application functionality in your mobile is not performance critical because most of them are interactive with a human being, and human response system is really slow. Right? We respond in seconds, or maybe you guys are younger, you may be doing say 300 milliseconds, not more than, not better than that. But the system operates at microsecond. So for applications on mobile, time is not the primary criteria. The important criteria is space, because you do not have much space. And there too, the optimization is of a different kind, because in a mobile, the same storage keeps your code as well as your runtime. Right? You do not have a concept of a hard disk where you can keep everything, almost infinite things, and bring it here. So the footprint of a code is a critical parameter. So in some cases, you may be optimizing for footprint, that is, the code should be short, because that has to permanently stay in your SD card. But memory in general is a sensitive matter. But the most sensitive is power. Most of the later smartphones now keep on prompting you, okay. I mean, you have your Google Photos on the system and it is draining your battery and so on. Because power is a very critical thing. So you might want to sacrifice a lot of time performance for better power performance, because you don't need to do things that fast, but you need to conserve power. So optimization is a very complex game of things. But at the core, it always means that optimizing something is optimizing for one or more resources, keeping the semantics same. If the semantic changes, it's not an optimization. And therefore, it is extremely difficult to do an automated optimization before semantic analysis. So you have to go up to that stage. And once you have come to the semantic analysis, you may do it on the syntax tree, on the parse tree, on the quad, tree address code, on assembly. Different options come up. And actually, different optimizations work well at different representation. That is why you have so many different things to do. And a lot of analysis for that needs to be done. And that is all that gamut that we are going to learn about. That's the excitement of the entire course. The initial part is a very well structured, very strong theory you have to understand, so that you know that if you have a correct program, you have a correct semantic representation. And the later part is somewhat exploratory, creative. It depends on what you can think of and do a better optimization. That was a little long answer to your short question, but does it answer your question?
Yes, sir, it does.
Okay.
Thank you.
Welcome. Any other question?
Sir, is the intermediate code generator dependent on the source language?
Intermediate code generator may not be dependent on the source language. It may be, but often it's not, because the intermediate code generation is happening from the syntax tree or parse tree. So by the time you have made the parse tree, semantically consistent, you have more or less got the language independence. But some bit of influence may stay, because some language, for example, may have a specific operator which is not there in other language, and so on. Like some languages have an exponential operator, which you will not have a representation of exponential operator in your 3 address code, because it's not it's not usually available. So you'll have to have a small translation done there. So those kind of influences little bit may be there. But grossly, once you have gotten the standardized tree representation for after the semantic analysis, you are done with the source language. Does that answer?
Yes, got it.
Any other question? Okay. Then Pralay, is there anything else to share? Otherwise, I think we can close for today.
No, it's fine. So actually, we will update the few dates on the assignments and on the test. So that
Sure.
after modifying that one, I will upload in the Moodle page.
Sure. Okay. So I've already shared the overlay with you.
Yes, I have.
You can directly edit on that. Okay. So thank you, friends, very much. It is really nice to meet you again, though I'm not getting to see your faces. I do not know almost none of you by face. Anyway, so have a good day. And we are closing here. From the next theory class, we will start discussing from the beginning as the topics we have given. Broadly, we have done a sharing between the theory lectures. In the initial part, in the front end, Professor Mitro would be taking the lectures, and I would be helping him. And in the back end, I would be taking the lectures, and Professor Mitro will support. So this is the kind of presentation schedule. Otherwise, everything remains same. You don't really have to worry about it, but I just wanted you to know that this is how we have planned to take the course forward. And we both will be there in the laboratory session starting day after tomorrow. And Professor Mitro will, please be on time and be present. Professor Mitro will start at 2:30.
Yes. So 2:30 day after tomorrow.
So day after tomorrow, 2:30 we will start. So please be on time, because Professor Mitro is going to talk about the VM as well as the assembly language and other details required for the laboratory, and you'll get your first laboratory assignment day after. Okay?
And one small announcement, one of you just sent an email to me indicating that some of you probably is coming back to the campus. So they will be starting on 16th and come back on 17th. And also since 19th, the next week Thursday, we have a holiday. So first assignment will be for 2 weeks. So 12 to 26. So don't worry about it. Okay. So even if you come back to the campus, so you will have you will have plenty of time, I should say, for your assignment one. Don't worry about that one. And apart from that one,
I missed to take care of the holidays in the scheduling. So
yes,
please have to.
I noted that, and now I am changing.
You'll have to change those dates.
Yes.
Yeah. Okay then. Thank you very much. So have a nice day. We'll close this session. Bye.